So our basic building blocks are the elements. Well, the smallest part of an element is an atom. The discussion about matter and how it was organized dates way back into ancient Greek and Roman times. There are two competing theories. One was the continuous theory of matter, and the other one was the discontinuous theory of matter. The continuous theory of matter said that if you kept breaking matter apart, you would never get to a smallest part of matter. The discontinuous theory of matter stated that if you kept breaking things apart, you would have eventually come to a smallest part of matter. And so the debate went on about these things, but unfortunately back in those times they didn't do much experimenting. And the idea that even the term atom dates back to these times. Now, fortunately, once they did start doing some experimentations, remember that once you collect data, you can develop laws, things that always are true. And so there were a few of these in particular that needed some explaining. So first was the law of constant composition, which said that if you took a sample of water, it didn't matter where you got the water from, as long as it was pure water, or the amount of water, that the composition of of hydrogen and oxygen would be exactly the same. The other one was the law of conservation of mass. It said that in any ordinary chemical or physical change, the mass was conserved. The mass didn't change. So these theories, or these laws, were in need of a theory. In 1808, an English scientist, John Dalton, proposed his atomic theory. You can find this in your book. I'm not sure if it's on page 88 anymore or not, but you can definitely find the parts to his theory. The first one was that elements are made up of tiny particles called atoms. The second was that atoms of a given element are identical. The atoms of a given element are different from those of any other element. Atoms of one element combine with atoms of another element to form compounds. A given compound always has the same relative number and types of atoms. And finally, that atoms are indivisible in chemical processes. So again, this theory, his atomic theory, explained the laws that had been developed as a result of numerous experiments. So his model depicted the atom as a solid, indestructible sphere. So pretty easy to visualize. Later in the 1800s, actually much later in the 1800s, an English physicist, J.J. Thomson, worked with something called Crookes tubes, which showed the existence of negative particles. These particles referred to are called electrons. Basically, what J.J. Thomson did was he evacuated a tube and created a large charge differential in the tube, one side being positive, one side being negative, and generated a beam of these particles going through that tube. And again, the term he gave to these particles were electrons. He knew that the electrons that were being produced would bend towards a positively charged plate. And so he knew that those electrons were negatively charged. So therefore, his model of the atom, as described by William Thomson, which is another different Thomson. William Thomson was more of a nobility type. And when he was reading about J.J. Thomson's model, he said that it sounded to him a lot like plum pudding. Well, that name stuck. And so this is referred to as the plum pudding model of the atom. So you can imagine these negatively charged particles embedded in a sphere of positive charge. And so this was the plum pudding model, which again existed around the late 1800s. In 1911, actually an Australian, Ernest Rutherford performed his famous gold foil experiment? He started out with a piece of gold foil, and he put a detector on the opposite side of the gold foil from a source of alpha particles. Now, so the picture here shows the detector all the way around the gold foil. At first, it was just on the opposite side of the gold foil because that's the only place that he thought these alpha particles were going to end up. However, quite by accident, his research assistant, Hans Geiger, who is more commonly known as developing the Geiger counter, happened to have left the detector off to the side of the gold foil. And they found that the alpha particles were still striking the detector. So they changed their experimental setup and put the fluorescent detector all the way around the gold foil, and found that while most of the alpha particles went straight through and hit the opposite side of the detector, there were a few that were scattered off at angles, and some of them would even bounce back off the gold. The result of this experiment led to the nuclear atom, in which most of the mass of the atom was located in a small central region called the nucleus. So rather than having all that positive charge as the main bulk of the atom, all that positive charge is going to be located in the nucleus. Now, there was a big problem with this. All the mass being positive, being located in the nucleus, created quite a dilemma because there was the feeling that there was no way you could get all that positive charge in that concentrated of a space in the nucleus. So Rutherford had to create a new type of force, something that was unimaginable at the time, that could hold all of those positive charges that close together. And he called that the nuclear force. We currently use that nuclear force for some very very large quantities of energy. So you might think a little bit about what that energy might be. In 1918, Rutherford called those positive particles in the nucleus protons. So, and again, at this point, we still didn't have neutrons. So by 1918, so this is less than 100 years ago, we still didn't even know that neutrons existed. Again, here's a depiction of what Rutherford was proposing for the structure of the atom. So you can see in the diagram on the left, you have the nuclei, which in this picture are actually rather large compared to the atom. The picture on the left. If you look over on the right, you can see that the size of the atom is anywhere from 1 to 5 angstroms, an angstrom being 10 to the minus 10th meters. And the nucleus is actually 10 to the minus 4th angstroms. So there's a magnitude of about 2,000 times. The nucleus is 2,000 times, or up to from 2 to 10,000 times smaller than the actual atom itself. So by this account, if you look back at the picture on the left, most of those alpha particles would just go right through the gold foil. Very few of them were going to actually come in contact with the nucleus and bounce back off, because most of the atom is empty space. And again, finally, in 1932, Rutherford and Chadwick determined that the nucleus must also contain neutral particles. At this time, they called those neutrons. We'll spend quite a bit of time later on in a future unit on the arrangement of the electrons around the nucleus. That's going to be most important in terms of determining and understanding the chemical properties of the individual atoms of different elements.